When we look into space, the brightest objects seem to stand apart. A star burns against an open sky. A galaxy glows as an island of light. A cluster appears as a distant gathering, separated from the next by stretches that seem almost empty. But this impression comes from the limits of human sight. On the largest scales, galaxies are not scattered at random. They gather along long, branching structures that cross the observable universe. These structures meet at crowded intersections, spread into broad walls, and curve around immense regions containing far less matter. Together, they form the cosmic web. The name describes its appearance, but not its full nature. This is not a web made only of visible galaxies. Most of its framework cannot be seen directly. Dark matter supplies much of the gravitational structure. Thin gas fills and surrounds its strands. Galaxies shine within it like small lamps, revealing parts of a far larger architecture. A single filament may extend for tens or even hundreds of millions of light years. Several can converge around a galaxy cluster, feeding matter toward one of the densest environments in space. Between them lie cosmic voids, regions so large that light can travel through them for many millions of years, while passing relatively few galaxies. The universe, seen at this scale, has a texture. There are knots where matter has collected. There are strands where galaxies and gas continue to move. There are sheets that divide one low-density region from another, and there are open volumes where gravity has drawn much of the material away. None of this appeared fully formed. More than 13 billion years ago, the young universe was much smoother than it is now. Matter and radiation were distributed with remarkable evenness, though not with perfect uniformity. Tiny differences were present. Some regions held slightly more matter than others. Those small differences became the beginning of everything we now recognize as cosmic structure. A region with a little more matter also possessed a little more gravitational pull. It gathered additional material. As it grew denser, its attraction became stronger. Over immense spans of time, matter moved toward matter, while the expansion of space continued around it. Gravity did not pull equally in every direction. Material collapsed first along one direction, creating flattened structures. It then gathered along another, producing filaments. Where several filaments met, dense nodes developed, and within those nodes, the largest galaxy groups and clusters began to assemble. The pattern was shaped by dark matter long before many of its visible galaxies had formed. Ordinary matter followed this underlying gravitational landscape. Gas collected inside dark matter, halos, cooled and helped create stars. Galaxies emerged within a structure that was already guiding where they could grow and how they would meet. Even now, that process has not ended. Matter continues to leave less crowded regions. Gas moves through filaments. Galaxies approach groups and clusters along preferred directions, rather than arriving from every part of the sky equally. The web is not a fixed diagram. It is an evolving system, stretched by cosmic expansion and reshaped by gravity. Our own galaxy belongs to this architecture. The Milky Way, the local group, and the larger concentrations of galaxies around us occupy one small part of a network extending far beyond anything a single telescope image can contain. Tonight, we will begin to trace that network. We will move outward from individual galaxies to clusters, from clusters to filaments, and from filaments to the broad pattern of the universe itself. And as the familiar points of light fall into place, the apparent emptiness between them will begin to look different. To understand the cosmic web, it helps to begin before there were galaxies. The early universe did not contain stars, planets, or the long chains of structure we see today. It was filled with hot matter and radiation, expanding and cooling together. For a time, light could not travel freely. Electrons moved among atomic nuclei, scattering photons again and again. Space was bright, dense and opaque, more like the interior of a glowing fog than the transparent universe we know. As expansion continued, the temperature fell. About 380,000 years after the beginning, electrons joined with nuclei to form neutral atoms. Photons were then able to travel across space with far fewer interruptions. That released light, still detectable today, as the cosmic microwave background. This background is remarkably even. Its temperature varies only by tiny amounts from one direction to another. Yet, those differences matter. They preserve a faint record of regions that contained slightly more or slightly less material when the universe was still very young. The variations were small enough that, without gravity, they might have remained almost unimportant. Gravity made them grow. Where matter was a little denser, the gravitational pull was also a little stronger. Material moved inward, increasing the density further. Regions with slightly less matter lost part of their contents to their surroundings and became more rarefied. Over millions and then billions of years, these early imbalances widened. The process did not create matter. It rearranged it. Dark matter played the leading role because it does not interact with light in the way ordinary matter does. It could begin gathering through gravity while normal matter was still strongly influenced by radiation. As the universe cooled, gas increasingly followed the gravitational wells that dark matter had already begun to form. The first version of the web was therefore invisible. It existed as a developing pattern of density, a landscape of shallow valleys and low ridges in the distribution of dark matter. Later, gas settled into the same framework. Stars ignited inside the densest concentrations. Galaxies appeared, giving light to parts of a structure that had been growing long before anything shone within it. The shapes that emerged were not arbitrary. Gravity acts in all directions, but the matter around a growing region is rarely distributed with perfect symmetry. A cloud of material may be compressed more strongly along one axis than another. Collapse tends to occur first along the direction where the gravitational gradient is greatest. A broad region can flatten into a sheet. The sheet can then narrow into a filament. Along the filament, material can continue toward a dense knot where several streams meet. This sequence helps explain why large-scale matter does not simply gather into isolated spheres. The universe contains elongated and flattened structures because gravitational collapse unfolds unevenly across an already uneven field. The resulting pattern is sometimes described through a landscape of peaks and valleys. The highest peaks become sites of galaxy clusters. Lower ridges become filaments. Broad slopes become sheets. The deepest low-density basins develop into voids. These features are connected. A void does not sit apart from a filament. As matter leaves an underdense region, it contributes to the walls and strands around it. A growing cluster is fed by the filaments that enter it. The web is one continuous redistribution of material, seen at different densities. Computer simulations make this transformation visible. Researchers begin with a model of the early universe, whose tiny fluctuations match observations of the cosmic microwave background. They allow gravity and cosmic expansion to operate over simulated time. At first, the model appears almost uniform. Then faint clumps form. The clumps stretch into chains. Chains connect into networks. Open regions expand between them, while dense nodes grow where several branches intersect. When ordinary gas physics is added, the simulations become more complex. Gas can heat as it falls into gravitational wells. It can cool and condense. Stars can form. Exploding stars and active galactic nuclei can push energy back into surrounding space. Yet, beneath all these processes, the large pattern remains recognizable. Dark matter supplies the framework. Gas follows the framework imperfectly. Galaxies illuminate selected parts of it. This is why maps of galaxies can reveal the cosmic web, even though galaxies account for only a limited fraction of its total mass. astronomers survey large volumes of space and measure the redshifts of many galaxies. A redshift helps estimate how cosmic expansion has carried a galaxy away from us, and therefore how far away it lies. By combining direction and distance, researchers build three-dimensional maps. In these maps, galaxies do not fill space evenly. They form arcs, walls, threads, and crowded junctions. Long corridors of low density separate one concentration from another. Some early galaxy surveys revealed this pattern in narrow slices of the universe. Later surveys mapped far larger regions, placing millions of galaxies within an expanding three-dimensional picture. The maps can look almost biological, though the resemblance is only visual. There is no organism directing the network and no intention within its shape. It is the result of simple physical ingredients acting over immense time. Initial density, variations, dark matter, gravity, expanding space, and ordinary matter responding to the environment these forces created. Even the expansion of the universe contributes to the form. On the largest scales, space itself continues to expand. Bound systems such as galaxies and many galaxy clusters resist that expansion internally because their gravity is strong enough to hold them together. Between these dense regions, however, distances grow. Voids expand more rapidly than crowded regions because they contain less matter to slow their local expansion. As they enlarge, they press the remaining material toward their boundaries, sharpening the contrast between open regions and the structures around them. The web becomes more pronounced with time. Dense areas grow denser, sparse areas grow emptier. But the development is gradual, and it is never completely finished. A filament seen today is part of a history still in motion. The galaxies within it may be falling toward a cluster. The gas between them may be warming as it is compressed. The dark matter halo surrounding the structure may still be gathering material from nearby space. The architecture has no fixed edge. A narrow strand can merge into a broader wall. A wall can divide neighboring voids. A cluster can sit at the center of several filaments, while also belonging to a larger concentration extending far beyond it. Scale changes the view. Up close, there are stars and clouds of gas. Farther out, there are galaxies and groups. Beyond them, individual systems become points within a larger design. And at the broadest level, the universe begins to resemble a connected pattern shaped from fluctuations that were once almost too small to notice. The bright galaxies are the visible record. The deeper structure lies around and between them, carrying the memory of how matter first began to gather. The cosmic web cannot be photographed in a single image. No telescope can step far enough away to see the entire pattern at once. Every observatory is located inside the structure it is trying to map, carried with the Milky Way through one small region of the network. Astronomers must reconstruct the web from many partial views. The most direct method begins with galaxies. A telescope records their positions across the sky, and a spectrograph separates their light into wavelengths. Within each spectrum are familiar patterns created by atoms in stars and gas. When those patterns are shifted toward longer wavelengths, astronomers can estimate how strongly the expansion of the universe has stretched the light during its journey. This measurement is called redshift. For distant galaxies, a larger redshift usually corresponds to a greater distance. By combining a galaxy's direction with its redshift, researchers can place it within a three-dimensional map. One galaxy contributes a single point. 1,000,000 galaxies begin to reveal a landscape. The first large redshift surveys changed the way the nearby universe was imagined. Instead of a nearly uniform field of isolated systems, the maps showed galaxies gathered into long bands and curved surfaces. Dense clusters appeared where several structures crossed. Broad spaces between them contained far fewer luminous objects. Some survey maps were shaped like thin wedges, because telescopes had measured a narrow strip of sky. extending outward through distance. Within those wedges, galaxies formed patterns that looked like foam seen in cross-section. Bright concentrations surrounded large openings, while chains of systems connected one crowded region to another. The appearance was striking, but the reconstruction was not simple. Redshift does not measure distance alone. A galaxy also moves through space because of the gravity around it. It may be falling toward a nearby cluster, moving along a filament, or orbiting within a group. This local motion adds to or subtracts from the redshift caused by cosmic expansion. As a result, a redshift map is slightly distorted. Inside galaxy clusters, members move rapidly in different directions. When plotted using redshift as distance, the cluster can appear stretched along the observer's line of sight, even though its true shape may be more compact. These apparent extensions are sometimes called fingers of God. On larger scales, another distortion appears. Galaxies falling toward a dense region can make the surrounding structure look compressed in redshift space. The pattern carries information about how matter moves under gravity, but it must be carefully interpreted before it can become a reliable map. The distortions are not merely errors to remove, they reveal motion. A galaxy's position shows where matter has gathered. Its peculiar velocity, the motion remaining after cosmic expansion is accounted for, shows how gravity continues to reshape that region. From these motions, researchers can test models of structure growth. They can compare how quickly matter appears to be falling into dense areas with the rate predicted by different cosmological models. The web becomes both an object and a process. Its shape tells us where matter is. Its motion tells us where matter is going. Galaxies, however, reveal only part of the architecture. They form most readily in regions where gas and dark matter have already reached sufficient density. Some filaments contain many galaxies and stand out clearly in surveys. Others are thinner, warmer, or less developed, carrying matter that has not formed bright systems. To trace those fainter regions, astronomers use background light. A distant quasar can serve as a lamp, shining through intergalactic space. Quasars are powered by material falling towards supermassive black holes in the centers of remote galaxies. Their light may travel across billions of light years before reaching Earth. Along the way, it passes through clouds of hydrogen. Each cloud removes a small amount of light at a particular wavelength. Because the universe is expanding, clouds at different distances produce absorption at different positions in the quasar spectrum. The result is a sequence of narrow absorption features known as the Lyman alpha forest. Each feature marks hydrogen, somewhere along the line of sight. One quasar gives astronomers a thin sample through the universe, like a single core drawn through a deep layer of ice. Thousands of quasars provide many parallel samples. When their sightlines are combined, the distribution of hydrogen between galaxies begins to emerge. This method is especially useful at earlier cosmic times, when intergalactic hydrogen was denser and the light from distant quasars passed through a younger of the web. The forest does not show filaments as clean glowing strands. Instead, it records variations in absorption. Denser regions remove more light. Thinner regions remove less. Statistical reconstruction turns those variations into a three-dimensional field, revealing where gas was concentrated across enormous volumes of the young universe. In this way, astronomers can map structures that contain no bright galaxy at all. They can follow the web through material that would otherwise remain nearly invisible. Another approach uses gravity itself. Any concentration of mass bends the path of passing light. A galaxy cluster can distort background galaxies into arcs. Smaller and more widely distributed structures produce subtler changes, stretching the apparent shapes of distant galaxies by amounts too small to recognize in a single object. When the shapes of many background galaxies are averaged together, a pattern appears. This is weak gravitational lensing. It allows researchers to estimate the distribution of mass without requiring that the mass emit light. Dark matter, diffuse gas, galaxies, and clusters all contribute to the gravitational field. The lensing map therefore traces the structure more directly than a map based only on visible galaxies. Weak lensing is difficult because galaxies already come in many shapes. A single elongated galaxy may be naturally elongated, gravitationally distorted, or both. Astronomers cannot know its original form, but across millions of galaxies, random orientations tend to average out, while a shared lensing signal remains. The effect is small, and the measurements demand careful control of telescope optics, atmospheric blurring, detector behavior, and image processing. Yet the result is powerful. A redshift survey maps light, weak lensing maps gravity. When the two agree, the bright galaxies can be seen occupying the deeper structure of matter. When they differ, the difference may reveal how galaxy formation depends on environment, or how ordinary matter is displaced by energetic processes. Galaxy clusters provide some of the clearest intersections. A massive cluster often sits where several filaments meet. Its gravity draws galaxies and gas inward from different directions. In images, the surrounding filaments may be difficult to separate from the background, but their influence appears in galaxy positions, lensing patterns, gas temperatures, and motion. Matter does not fall straight toward the center from every angle. It arrives along preferred corridors. Smaller groups may travel down the same filament before merging with the cluster. Individual galaxies can enter together, carrying the history of an earlier environment with them. Gas may be compressed and heated as it approaches, creating a transition between the cooler intergalactic medium and the hotter atmosphere inside the cluster. This movement is sometimes described as cosmic accretion. The word suggests accumulation, but the process has structure. Matter is guided by the surrounding gravitational field. A cluster grows not as an isolated sphere, drawing from as a node fed by connected strands. Some of the largest known structures are identified through the distribution of clusters, galaxies, and quasars across wide regions. Their apparent size can be immense, but defining a structure at this scale requires care. A connected chain in a survey does not always mean that every part is gravitationally bound. Cosmic expansion may eventually carry distant sections apart. The name of a wall, complex, or supercluster can describe a recognizable pattern without implying that it will remain a single object forever. Even our position within the nearby universe has been revised as mapping has improved. The Milky Way belongs to the local group, a small collection dominated by the Milky Way and the Andromeda Galaxy. The local group lies near larger concentrations of galaxies and moves under their combined gravitational influence. Beyond the nearest groups and clusters, the surrounding pattern includes broad sheets, filaments, and low-density regions. One nearby void contributes to the motion by containing less matter on one side of us. Dense regions attract, while underdense regions provide less opposing pull. The movement of our galaxy is shaped by this imbalance across scales far larger than the Milky Way itself. You can think of the local universe as a gravitational terrain. The Milky Way is not stationary upon it. The galaxy moves within the local group. The local group moves relative to nearby structures. Those structures participate in broader flows shaped by the distribution of matter across hundreds of millions of light years. There is no single fixed platform beneath the motion, only nested relationships. A star travels around a galaxy. A galaxy travels within a group. A group moves along the surrounding web, and the web develops while space expands. Mapping these layers requires different instruments, because no one kind of observation can reveal them all. Optical surveys count galaxies. Spectroscopy measures redshifts. Radio observations trace neutral hydrogen. X-ray telescopes detect hot gas in clusters. Microwave measurements reveal pressure from energetic electrons through their effect on ancient background light. Gravitational lensing traces total mass. Quasar absorption exposes diffuse hydrogen between luminous systems. Computer simulations connect the measurements into a physical history. Each method sees a different component. Together, they show that the web is not a decorative arrangement of galaxies. It is the main environment in which galaxies form, receive material, interact, and change. A map of the cosmic web is therefore more than a map of location. It is a record of gravity acting across time. The dense knots show where matter has accumulated. The filaments show the routes along which accumulation continues. The voids show where material has departed, and the faint absorption lines in distant light preserve the presence of gas that has never entered a star. The architecture becomes clearer, not because the universe grows brighter, but because astronomers learn how to read what brightness alone cannot show. A filament is not a single thing. It is a region where several forms of matter overlap, each responding to gravity in a different way. Dark matter provides most of the mass. It gathers into elongated halos and connected bridges that extend between groups and clusters. Ordinary matter follows, but not perfectly. Gas can be compressed, heated, cooled, ionized, and pushed outward by events inside galaxies. Stars remain locked inside galaxies, while much of the gas occupies the much larger spaces between them. Seen only in visible light, a filament may look like a chain of galaxies. Seen through gravity, it is broader. Seen through gas, it becomes more varied. Near its center, the density may be high enough to guide groups of galaxies toward a cluster. Farther from the axis, the material becomes more diffuse, blending into the lower density regions around it. There is rarely a sharp boundary where a filament ends and empty space begins. Its edges are gradual. Matter becomes thinner, colder, and more difficult to detect. The dark matter component cannot radiate light. Its presence is inferred through the motions of galaxies, through lensing, and through the way simulated universes reproduce observed structure when dark matter is included. Without that invisible mass, the web would not have developed in the same way. Ordinary matter alone would have been too strongly coupled to radiation in the early universe and too limited in total mass to create the observed pattern on the same schedule. Dark matter began building the framework first, allowing gas to settle into deepening gravitational channels. After the universe became transparent, yet the gas does not remain cold as it falls. Gravity changes motion into heat. Material moving toward a filament can be accelerated by the growing structure. When streams collide or are compressed, shocks can form. Particles begin moving more rapidly in random directions, and the temperature rises. Some intergalactic gas remains relatively cool by cosmic standards, near 10,000 degrees. Other parts are heated to hundreds of thousands or millions of degrees. This hotter material is often described as the warm-hot intergalactic medium. The name covers a wide range of conditions. Warm and hot are relative terms here. Gas at 1,000,000 degrees is far beyond anything familiar on Earth, but it can still be difficult to observe because its density is extremely low. Temperature alone does not make something bright. A thin gas may contain particles moving at high speed, while producing very little radiation. Collisions are too infrequent for the material to glow strongly. The gas can fill enormous volumes and still remain almost absent from ordinary images. This creates one of the central observational problems of the cosmic web. Astronomers can estimate how much ordinary matter should exist from measurements of the early universe. They can also count how much is present in stars, cold gas, galaxies, and galaxy clusters at later times. For many years, those inventories did not match. A substantial share of normal matter seemed to be missing from the nearby universe. The matter was not believed to have vanished. It was expected to exist in a form that was difficult to detect, spread through filaments and low-density regions as ionized gas. The cosmic web offered a likely hiding place. As observations improved, evidence increasingly supported this picture. Diffuse gas was found through faint absorption lines, weak X-ray emission, and subtle effects on background radiation. The missing matter problem became less a question of whether the material existed, and more a question of how completely it could be measured. Most of this gas contains no neutral hydrogen. At high temperatures, electrons are separated from atomic nuclei. The gas becomes ionized, and many familiar spectral signatures weaken or disappear. Researchers, therefore, look for particular ions that form under specific conditions. Oxygen can lose several of its electrons in warm or hot environments. The absorption lines of these ions can appear in the ultraviolet or X-ray spectra of bright background sources. When the light from a quasar passes through a filament, a small fraction may be removed at a wavelength associated with highly ionized oxygen. The signal can be extremely faint. It may require long observations and careful separation from absorption produced within our own galaxy or by unrelated material along the line of sight. A detection reveals only one narrow path. It says that gas exists somewhere between the quasar and the telescope at a particular redshift. Many such paths are needed before the larger distribution becomes clear. Emission is even more difficult. Gas within a filament can radiate X-rays if it is hot enough, but the surface brightness is low. The glow may be overwhelmed by the background sky, by detector noise, or by emission from the outskirts of nearby clusters. The strongest signals are often found where filaments connect to massive clusters. There, gas is denser and hotter. The gravitational potential is deeper. Matter flowing inward can be compressed more strongly, making the filament easier to observe. These regions are useful, but they are not fully representative. A bright bridge between two clusters may be only the most visible section of a much longer, fainter structure. The rest continues beyond the image, below the sensitivity of the instrument. Microwave observations offer another way to detect the gas. The cosmic microwave background passes through the entire observable universe. When its photons encounter energetic electrons, their energies can be shifted slightly through scattering. This effect is small, but it carries information about the pressure of the intervening gas. Galaxy clusters produce a strong version because they contain dense, hot atmospheres. Filaments create a weaker signal. By combining observations of many pairs of galaxies or clusters, astronomers can average away random noise and reveal the shared pressure pattern between them. No single filament must be obvious. The signal emerges statistically. This kind of measurement has changed the meaning of invisibility. A structure too faint to image directly may still leave a collective imprint. Its gas can be detected not because one object stands out, but because thousands of similar regions produce the same subtle effect. The filament becomes visible through repetition. There are also differences within the gas itself. Near galaxies, heavy elements can be present. These elements were created inside stars and released through stellar winds, supernova explosions, and the activity of galactic nuclei. Once expelled, they can travel beyond the visible boundaries of a galaxy and mix with the surrounding medium. A filament is therefore not composed only of primordial hydrogen and helium. Parts of it have been enriched by generations of stars. The distribution is uneven. Gas closer to galaxies may contain more heavy elements. More isolated material may preserve a simpler composition. Turbulence, outflows, and gravitational motion can mix these regions, but the mixing is incomplete. The web carries both early cosmic material and the products of later stellar history. A single stream can contain atoms formed in very different eras. Hydrogen may have existed since the first minutes after the beginning. Carbon or oxygen may have been produced billions of years later inside stars. Both can now move through the same intergalactic current. The relationship between galaxies and filaments is not one way. Galaxies receive material from the web. They also return material to it. Gas can fall into a galaxy's surrounding halo, cool, and contribute to star formation. Later, energy from young stars, supernovae, or a central black hole can push some of that material outward again. These outflows may slow future star formation by removing gas. They can also heat the surrounding environment and distribute heavy elements into larger volumes. The boundary between a galaxy and the web is therefore active. Matter crosses it in both directions. Around each galaxy lies a diffuse region called the circumgalactic medium. It extends well beyond the visible disk or central collection of stars. This gas acts as an intermediate zone between the galaxy and the larger filament. Material from the web can enter the circumgalactic medium before reaching the galaxy. Material leaving the galaxy can pass through the same region on its way outward. The circumgalactic medium is not simply an atmosphere. It is a reservoir, a filter, and a record of exchange. Its temperature and density depend on the galaxy's mass, star formation history, environment, and past interactions. In crowded parts of the web, surrounding gas can be stripped, compressed, or heated. In less dense regions, a galaxy may retain a larger share of its extended material. This helps explain why a galaxy's location matters. Two galaxies with similar masses can evolve differently. If one lives inside a rich filament near a cluster and the other lies along a thinner strand, environment changes the supply of gas. It changes the frequency of encounters. It changes the pressure of surrounding material. And it changes how easily a galaxy can hold what it receives. Filaments are not uniform roads delivering the same conditions everywhere. They are physical environments with gradients. Some are narrow and cold, some are broad and heated. Some contain many galaxies. Some are defined mainly by dark matter and diffuse gas. Some connect massive clusters. Others fade into sheets before reaching any crowded node. Their internal motions also vary. Gas may flow along the filament toward a cluster. It may fall inward from the sides. It may be stirred by merging groups or by energy released from galaxy. The dark matter follows gravity without pressure, while gas resists compression, forms shocks, and develops turbulence. The two components occupy the same general structure, but do not trace it in exactly the same way. This difference matters when astronomers compare simulations with observations. A dark matter-only simulation can reproduce the broad pattern of the web. But to understand where ordinary matter is found, researchers must also include gas dynamics, radiation, cooling, star formation, and energetic feedback. Each added process changes the small-scale distribution. Gas may be pushed out of shallow gravitational wells. It may remain hot around massive halos. It may cool rapidly in dense regions. It may become enriched with heavier elements. The largest structure survives these complications, but its contents become richer and less predictable. There is a calm scale hidden in this complexity. A filament can contain countless galaxies, yet much of its volume is occupied by particles separated by distances that would feel empty in any laboratory. Its matter is sparse, but its total mass is immense because the structure extends so far. A few particles in every cubic meter, repeated across millions of light years, become a major part of the universe's ordinary matter. Density and importance are not the same. The brightest places do not contain everything. Much of the cosmos exists between them, spread thinly through regions that shape motion without drawing attention to themselves. As telescopes become more sensitive, the web appears less like a skeleton made of galaxies and more like a layered environment. Dark matter forms the gravitational foundation. Gas records compression and heat. Heavy elements preserve the history of stars. Galaxies mark the dense points where matter became luminous And between those points, the filament continues, carrying material towards structures still in the process of becoming. A galaxy does not move through the cosmic web like a ship crossing an open sea. It is formed within the current. Its dark matter halo grows from the same underlying structure as the filament around it. Gas arrives along paths shaped by gravity. Neighboring galaxies tend to appear where the same conditions have already gathered enough material to create them. The environment is present from the beginning. In the thinner parts of the web, a galaxy may spend much of its life with relatively few close neighbors. Its supply of gas can continue with limited disturbance. Stars may form across a disk for billions of years, guided more by internal processes than by frequent collisions. Closer to a node, the conditions change. The density of galaxies increases, groups begin to form. Relative motions become more complicated. Gas grows hotter. Encounters become more common, and the path toward a cluster can transform a galaxy before it reaches the cluster itself. This gradual change is sometimes called pre-processing. A galaxy may enter a small group while both are still moving along a filament. Inside that group, it can experience gravitational interactions, gas loss, or a merger. By the time the group reaches a large cluster, its members may already be very different from similar galaxies that remained farther away. The cluster does not create every change. Some of the transformation begins along the route toward it. A filament can guide galaxies into repeated proximity because their motions are not random. They are being drawn toward the same dense regions. Two galaxies moving along a shared strand may approach each other with lower relative speeds than galaxies moving inside the center of a rich cluster. Lower speeds can make gravitational encounters more effective. The galaxies have more time to pull on one another. Their disks can stretch into tidal tails. Gas can be compressed. Stars can be displaced. In some cases, the galaxies merge. A merger does not occur simply because two galaxies come near each other. Their trajectories, masses, speeds, and surrounding dark matter halos all matter, but the cosmic web creates places where encounters are more likely and where repeated interactions can occur over long spans of time. This makes filaments active regions of galactic evolution. They are not only channels carrying matter toward clusters, they are places where galaxies meet before arrival. The orientation of a galaxy can also preserve something of its relationship with the web. Galaxies rotate because the matter that formed them carried angular momentum. That rotation emerged from the uneven gravitational pulls of surrounding structures during collapse. The direction of a galaxy's spin is therefore connected, at least statistically, to the environment in which it formed. Researchers have found that galaxy spins can show preferred alignments relative to nearby filaments. The pattern is not identical for every galaxy, and it can change with mass, merger history, and local conditions. Lower mass galaxies may be more likely to rotate with their spin axes aligned along a filament. More massive galaxies may show a tendency toward a different orientation, with spins more often perpendicular to the filament. One explanation is that smaller galaxies grow through smoother inflow, receiving matter along the structure around them. Larger galaxies experience more mergers, and those mergers can rearrange angular momentum. The transition is not a strict boundary. It appears as a statistical tendency across many systems. A single galaxy can have a complicated history that does not follow the average. But when thousands are measured together, the influence of the larger structure begins to appear. The web leaves a trace not only in where galaxies are found, but in how they turn. Shape can carry another trace. Galaxies embedded in dense environments are more likely to have experienced interactions that alter their form. Spiral disks can be disturbed. Stellar orbits can become less ordered. Mergers can produce elliptical galaxies with little visible disk structure. Along a filament, the proportion of galaxy types often changes as the distance to a cluster decreases. Farther away, star-forming spirals may be more common. Closer to the node, passive galaxies with older stellar populations become more frequent. This does not mean that every spiral becomes elliptical as it travels inward. Several processes can reduce star formation without completely destroying a disk. The supply of fresh gas may decline. Gas already inside the galaxy may be consumed. The surrounding medium may remove material from the outer halo. Repeated gravitational disturbances may thicken the disk or alter its internal structure. The result can be a galaxy that retains much of its shape while becoming less active. A galaxy can fade before it changes form. The loss of star formation often begins with the loss of fuel. Stars form from cold, dense gas. If a galaxy continues receiving gas from the surrounding web, it can sustain new generations of stars. If that supply is interrupted, the remaining reservoir gradually decreases. Dense environments can cut off this inflow. A galaxy entering a group may find that the surrounding gas is too hot to settle efficiently. Its extended halo of cooler material may be stripped by interactions with the group medium. Without that outer reservoir, the galaxy continues forming stars for a time, but the process cannot be maintained indefinitely. This has been described as starvation or strangulation. The words are dramatic, though the physical process can be gradual. Nothing disappears at once. The galaxy simply stops receiving enough new material. Over hundreds of millions or billions of years, its bright young stars become less common. Blue light weakens. The stellar population grows older. The galaxy remains present, but its internal pace changes. Near a massive cluster, gas removal can become more direct. A galaxy moving through hot intra-cluster gas experiences pressure. The stars and dark matter are not strongly affected by this pressure, but the galaxy's own gas can be pushed backward and stripped away. This is ram pressure stripping. In some observed galaxies, the removed gas trails behind in long streams. New stars may form briefly within compressed sections of the tail, while the galaxy's disk loses the material needed for future star formation. The motion can create a striking imbalance. Stars continue on their gravitational paths. Gas responds to the surrounding medium. The two components, once moving together, begin to separate. A filament approaching a cluster can contain transitional environments where these processes first become important. The gas is not as dense or hot as it is in the central cluster, but it may already be changing the galaxies passing through it. Groups falling along the filament can carry their own hot atmospheres. Interactions between these groups, the filament gas and the cluster outskirts, create overlapping influences. It can be difficult to identify one cause. A galaxy may have lost part of its gas, a small group, undergone a close encounter, and then experienced stronger stripping near the cluster. Its present appearance becomes the record of several environments crossed in sequence. This is why distance from a cluster is useful, but not sufficient. Two galaxies at the same distance may have arrived along different paths. One may be approaching for the first time. Another may have already passed through the cluster and moved outward again. A third may belong to an infalling group with its own internal history. Position gives one moment. Orbit gives the larger story. Simulations help researchers follow these paths across time. A present-day map can show where a galaxy is now, but a simulation can estimate where similar systems came from, how long they spent in filaments or groups, and when their gas supply began to change. The result is not a perfect reconstruction of any individual galaxy. It is a physical comparison between populations and likely histories. Across these models, the web appears as a sequence of environments, rather than a set of separate categories: void, sheet, filament, group, cluster. Matter can move through these regions gradually, and a galaxy can be altered at each stage. The path is not always inward. Some galaxies are thrown onto wide orbits after close encounters. Some pass through a cluster and travel back toward its outskirts. Some move between neighboring filaments as the surrounding structure evolves, but the general flow of matter is toward denser regions. Voids lose material. Sheets feed filaments. Filaments feed nodes. Galaxies participate in this movement while carrying their own stars, gas, black holes, and histories. The central black hole can also respond to the environment. When interactions disturb a galaxy, gas may lose angular momentum and move inward. Some of it can reach the region around the central black hole. As the gas heats and radiates, the galactic nucleus becomes active. The energy released can affect the surrounding galaxy. Radiation, winds, and jets can heat or displace gas. In massive systems, this feedback may help prevent new material from cooling into stars. The environment can therefore influence a galaxy's center, and the center can influence the galaxy's future. Some of that energy escapes beyond the galaxy. Jets from active nuclei can extend into the circumgalactic or intergalactic medium. They inflate cavities, drive shocks, and redistribute energy across distances much larger than the visible stellar system. In dense nodes, repeated activity from many galaxies can alter the thermal state of the surrounding gas. The cosmic web shapes galaxies. Galaxies also modify the web. The effect is strongest on smaller scales and near dense structures. A galaxy cannot rearrange a filament hundreds of millions of light years long, but across billions of years, many galaxies can heat, enrich, and stir the ordinary matter within it. The dark matter framework remains dominant. The gas records the consequences. Heavy elements spread outward. Temperatures change. Some regions become more difficult to cool. Others receive fresh material from continued inflow. The exchange never becomes perfectly balanced. A galaxy can gain gas along one direction and lose it along another. It can form stars while also driving material outward. It can be drawn toward a cluster while orbiting within a smaller group. Several scales of motion coexist. Inside the galaxy, stars circle the center. Around the galaxy, gas moves through the halo. The halo travels along the filament. The filament channels matter toward a node, and the node grows within the larger expansion of the universe. From the surface of Earth, none of this motion is visible to the eye. A distant galaxy appears fixed. Its shape may seem permanent, but the image is one moment from a process that unfolds across timescales longer than human history. The spiral arms may be receiving gas. The outer halo may already be losing it. A companion may be approaching. A cluster may lie millions of light years ahead along the same strand. The galaxy's future is partly written in the structure around it. Long before it reaches the crowded center, the road has begun to change the traveler. Beyond the crowded knots and flowing filaments, the cosmic web opens into regions where matter is scarce. These are the voids. They are not completely empty. A few galaxies remain within them. Thin gas is still present. Dark matter has not vanished, but compared with the structures around them, voids contain much less material. Some extend for tens of millions of light years. The largest are even broader, enclosed by sheets and filaments that mark the places where matter has gathered more efficiently. A void can be imagined as a basin in reverse. Instead of collecting material, it has gradually lost part of what it once contained. Regions that began with slightly lower density exerted less gravitational pull than their surroundings. Matter moved away from them toward nearby concentrations. As this happened, the underdense region expanded. The growth of a void is therefore not separate from the growth of the web. The same motion that thins one region strengthens another. Matter leaving a void contributes to the walls around it. Those walls feed filaments. Filaments guide material toward nodes. The network becomes sharper because the low-density and high-density regions develop together. This creates a landscape of contrast. A galaxy cluster may contain thousands of galaxies within a relatively compact region. Nearby, a void of far greater volume may hold only a sparse population. Most of the volume of the universe lies in such low-density regions. Most of the matter does not. This difference between volume and mass is important. If the observable universe were divided by space alone, voids would occupy much of the map. If it were divided by where matter is concentrated, the filaments and nodes would dominate. The cosmic web is therefore both open and connected. Large areas contain little. Narrower structures contain much. Voids are difficult to see directly because they are defined by absence. Astronomers find them by mapping the galaxies around them and identifying regions where the number density falls below the surrounding average. Different methods can produce somewhat different boundaries because a void does not have a solid edge. Some are nearly spherical, others are elongated, compressed by nearby structures, or divided into smaller, underdense regions. Many are nested. A large void may contain smaller variation inside it, while belonging to an even broader, low-density environment. The classification depends partly on scale. A region can be empty compared with a galaxy cluster, while still containing more matter than the deepest interior of another void. There is no single density shared by all voids. Their histories differ. Some lie between growing walls and become squeezed over time. Others continue expanding, their interiors becoming more rarefied as matter moves outward. This leads to two broad evolutionary possibilities. A void surrounded by larger underdense regions may continue to grow and merge with its neighbors. Its boundaries become less distinct as several open regions combine. A smaller void embedded within an overall dense environment may be compressed by the stronger collapse occurring around it. It can be gradually erased as surrounding walls and filaments move inward. These behaviors are sometimes described as void in void and void in cloud evolution. The names refer to the larger environment. A void inside a broader void tends to expand. A void inside a denser region may be crushed. Even absence has a context. Galaxies that live within voids provide a useful comparison with galaxies in filaments and clusters. They tend to have fewer close neighbors. Major interactions are less frequent. Many retain gas and continue forming stars for long periods because the processes that remove or heat gas in crowded environments are weaker. Void galaxies are not primitive objects preserved unchanged from the early universe. They have their own mergers, internal evolution, stellar feedback, and dark matter halos, but their surroundings are less disruptive. This allows astronomers to study how galaxies develop when environmental pressure is reduced. Some void galaxies are small and blue with ongoing star formation. Others are more massive. A few lie in faint chains or miniature filaments inside the void itself, showing that the cosmic web does not end at the boundaries of the largest structures. It continues at lower density. Even a region described as empty can contain a finer network. This smaller architecture reflects the same basic process, operating with less material. Dark matter gathers, gas follows. Galaxies form where local conditions allow. The difference is not one of physical law, but of degree. Voids also affect motion. A dense structure pulls matter toward it. An underdenser region contributes less gravitational attraction from its direction. Together, these effects produce flows that can appear as if the void is pushing matter away. There is no repulsive force coming from the void. The motion arises because surrounding matter is pulled more strongly toward the denser side. From the viewpoint of a galaxy near a void boundary, the result can resemble outward movement. The distinction is subtle but important. Gravity remains attractive. The imbalance creates the apparent push. Our own cosmic neighborhood is influenced by nearby underdense regions in this way. The motion of the local group cannot be understood by considering only the nearest large concentration of galaxies. Low-density areas also matter because they reduce the pull from other directions. A galaxy's path is shaped by the full gravitational landscape. not only by what is present, but by what is missing. Voids provide another kind of scientific opportunity. Because they contain less matter, they have experienced less complicated gravitational evolution. Their interiors are closer to the smooth expansion of the universe than dense clusters are. This makes them useful for studying cosmology. Their shapes and distributions carry information about how structure grows, how gravity behaves across large distances, and how cosmic expansion changes over time. A perfectly spherical void, viewed in ordinary space, may appear distorted when mapped through galaxy redshifts. Part of that distortion comes from the motions of galaxies around its boundary. Another part can arise from the assumptions used to convert observed redshift into distance. By comparing the apparent shape with physical models, researchers can test whether the adopted cosmology is consistent with the data. Voids are also sensitive to the properties of dark energy, the name given to the process associated with the accelerated expansion of the universe. As expansion accelerates, it affects the growth of large-scale structure. Dense regions continue evolving under gravity, while voids can become increasingly dominant in volume. The detailed pattern depends on the balance between attraction and expansion. Measurements of void populations can therefore complement studies based on galaxies, clusters, and the cosmic microwave background. No single observation settles the nature of dark energy. The value comes from agreement among many independent methods. Voids add one more perspective. Their emptiness becomes data. Gravitational lensing can also be used to study them. A massive cluster bends background light toward itself. A void produces the opposite pattern relative to the average matter distribution. Because it contains less mass than expected for its volume, the light passing near it is deflected less than it would be in a region of average density. The signal is weak. A single void rarely produces a clear lensing pattern. But by stacking measurements from many voids, astronomers can detect the average effect. The result helps confirm that the galaxy-defined emptiness corresponds to a real deficit of matter, including dark matter. Again, absence leaves a measurable trace. The cosmic microwave background may also be altered slightly as its photons cross evolving voids and clusters. If the gravitational potential changes while a photon is passing through, the energy gained on entering may not exactly match the energy lost on leaving. The resulting temperature shift is very small. Detecting it requires comparisons across many large structures, and the interpretation can be difficult. Still, it offers another way to connect the visible web with the expansion history of the universe. Voids are not static hollows suspended between permanent walls. Their boundaries move. Their interiors expand. Small structures within them continue developing. Nearby filaments can bend, merge, or be drawn toward larger nodes. A present-day map captures only one stage. Far into the future, if accelerated expansion continues, distant regions of the web will become increasingly separated from one another. Gravitationally bound groups and clusters will remain intact, but structures that are not bound together will recede beyond practical contact. The cosmic web will not disappear locally. Its large-scale connected appearance will gradually become less accessible to any observer confined within one bound region. Light from remote filaments will be increasingly redshifted. Distant galaxies will fade from view. The broad architecture visible to present-day astronomy belongs partly to this era, when much of the surrounding universe can still be observed. There is something useful in returning to the present scale. The room around you may feel enclosed and still. Yet the planet is moving within a galaxy. The galaxy is moving within a local flow. And that flow is shaped by both crowded structures and open regions far beyond direct perception. A void hundreds of millions of light years away can contribute to the pattern of motion in its surroundings. An absence spread across enough space becomes physically important. The universe does not build structure only by gathering matter. It also builds structure by leaving regions behind. The filaments become visible because the voids widen around them. The walls become distinct because matter drains away from their interiors. The nodes grow because the surrounding network continues to feed them. What appears empty is part of the architecture. Without the open regions, the web would have no shape. The cosmic web is difficult to imagine because its largest structures do not fit comfortably within human intuition. A galaxy is already enormous. A cluster contains hundreds or thousands of galaxies. A filament can connect several clusters across distances so great that even light requires hundreds of millions of years to cross them. At that scale, familiar ideas of location begin to weaken. A filament is not a narrow thread in the ordinary sense. It may be several million light years across. Its length can be dozens of times greater. The galaxies within it are separated by distances that would make each one appear isolated if viewed on a smaller map. Only from far enough away does the connection emerge. Scale changes the meaning of closeness. Two galaxies can belong to the same filament while remaining millions of light years apart. Two clusters can be linked by gas and dark matter even though no visible bridge is obvious between them. The structure is real, but its continuity is expressed through gravity and density rather than through solid matter. This creates a problem for language. Words such as strand, wall, knot, and web are useful because they provide shape. They allow a listener to hold the idea for a moment. But each word also suggests something more compact and more sharply defined than the universe provides. A cosmic wall has no surface. A filament has no clean border. A node is not a point. The names describe patterns in a field. Matter becomes more concentrated in one region and less concentrated in another. The transition can be gradual over millions of light years. Astronomers, therefore, define structures using mathematical tools. Some methods follow the density field and identify ridges where matter is concentrated. Others connect galaxies according to their separation, linking nearby systems into chains. Some examine the geometry around each point, asking whether collapse has occurred along one direction, two directions, or three. Collapse along one axis can create a sheet. Collapse along two can create a filament. Collapse along three can create a node. The exact boundaries depend on the method and the scale being studied. A galaxy near the edge of a filament may be classified differently by two algorithms, even when both are applied correctly. This does not mean the filament is unreal. It means nature has not drawn an outline around it for our convenience. Clouds on Earth offer a smaller analogy. A cloud exists. Its position and shape can be described, yet its edge becomes less distinct when examined closely, fading through thinner droplets into surrounding air. The cosmic web behaves in a similar way, though the medium and scale are entirely different. Its structures are clear in aggregate and ambiguous at the margins. This uncertainty matters when researchers compare observations with simulations. To test whether a model produces the correct web, they must decide what properties to measure: the number of filaments, their thickness, their length, the density of galaxies within them, the distribution of void sizes, the masses of nodes, the alignment of galaxies, the temperature of gas, the strength of lensing. Captures the whole architecture. A simulation might reproduce the number of clusters while producing filaments that are too broad. Another might match galaxy positions but place too much gas in dense regions. A third may reproduce large-scale statistics while failing to form realistic individual galaxies. The comparison is layered because the web itself is layered. Dark matter determines much of the gravitational framework. Ordinary matter adds pressure, heat, radiation, chemistry, and feedback. Galaxies introduce histories that depend on mergers and star formation. Observations add selection effects because telescopes detect some objects more easily than others. A map of bright galaxies is not the same as a map of all galaxies. A map of galaxies is not the same as a map of mass. A map of mass is not the same as a map of gas. Each version is related, but none is complete. This is one reason simulations are so valuable. They allow astronomers to examine components separately and together. A simulated universe can show the dark matter field without stars. It can reveal gas temperature in colors no human eye could see. It can track a single galaxy backward through time. It can display the paths by which matter entered a cluster. Then those predictions can be compared with what telescopes actually detect. The process is not simply an attempt to create a beautiful resemblance. The goal is to test whether a set of physical assumptions can produce a universe like the observed one. The broad success is notable, starting from small early fluctuations and allowing gravity to act within an expanding universe dominated by dark matter. Simulations naturally form networks of voids, sheets, filaments, and nodes. No separate rule must be added to create the web. It emerges. The detailed contents are harder. Gas can cool rapidly and form too many stars if feedback is too weak. If feedback is too strong, galaxies may lose too much material. Black hole activity can heat cluster gas, but the timing and efficiency are difficult to model. Processes occurring near individual stars can influence the distribution of matter across galactic halos, creating a span of scale that no simulation can resolve completely. Researchers therefore use approximations for some small-scale processes. These approximations are called subgrid models. They represent events occurring below the resolution of the simulation, such as star formation inside dense molecular clouds or energy released by accreting black holes. The name sounds technical, but the idea is simple. A model cannot follow every atom. It must describe the average effect of processes too small to calculate directly. The challenge is to ensure that these approximations do not merely force the simulation to resemble observations while hiding incorrect physics. A useful model should match more than one result. It should reproduce galaxy populations, gas fractions, cluster temperatures, large-scale clustering, and other independent measurements without requiring a new adjustment for each one. The cosmic web provides a demanding test because it connects many scales at once. A change in how gas is expelled from galaxies can alter the matter distribution around halos. That can affect weak lensing signals. It can change the temperature of intergalactic gas. It can influence how much ordinary matter remains inside filaments. Small-scale physics leaves a large-scale imprint. The reverse is also true. The large-scale environment influences small systems. A galaxy forming near a node receives a different merger history from one growing in a void. Its gas arrives from different directions. Its halo may be stretched by surrounding structure. The web is not background scenery. It participates in the formation of what lies within it. This relationship can be followed back through cosmic time. In the younger universe, the web was less sharply developed. The density contrast between crowded and sparse regions was smaller. Filaments existed, but many were thinner and less mature. Clusters had not yet assembled much of their present mass. Galaxies were more actively forming stars because cold gas was more abundant and inflow rates were higher. As time passed, the network became more defined. Nodes grew, voids expanded, filaments became richer. More galaxies entered groups and clusters. The present web is therefore one frame in a long evolution. Looking farther into space also means looking farther into the past, because light requires time to travel. A galaxy seen 10 billion light-years away is observed as it was long ago. Large surveys can therefore map different stages of the web by selecting galaxies at different redshifts. The task becomes harder at greater distance. Galaxies appear fainter. Their positions are more difficult to measure precisely. The surrounding gas is harder to detect, yet the reward is a view of structure in formation. Instead of seeing only the mature network, Astronomers can watch its earlier outlines. Some of the most distant known concentrations are not yet relaxed clusters. They are protoclusters. Their galaxies occupy a broad region that will later collapse into a denser system. At the time observed, the members may still be separated by millions of light years and connected through a developing web. A protocluster is a future node seen before its assembly is complete. Its shape can be irregular. Several subgroups may be falling toward one another. Gas flows may extend across the region. Star formation can be intense because the galaxies still contain abundant fuel. Over billions of years, gravity will draw much of this material together. The eventual cluster is present only as a tendency. This is one of the deeper themes of the cosmic web. Structure can exist before it is finished. A filament can guide matter before becoming dense. A node can influence motion before becoming a mature cluster. A void can begin expanding before its boundaries are pronounced. The architecture is developmental. Its form is always partly about the future. The same is true on smaller scales. A galaxy entering a filament may be moving toward a group it will not reach for billions of years. Gas falling toward a halo may not form stars until long after it begins the journey. Gravity acts patiently. It does not require the structure to be complete before shaping what comes next. For much of human history, the night sky offered no hint of this arrangement. Stars formed patterns because observers connected them into constellations. The patterns were meaningful, but they were created from a two-dimensional view. The cosmic web is different. Its connections are physical. They are revealed only when distance is added to direction. And when matter is mapped across 3 dimensions, the first generations of survey astronomers transformed isolated points into a spatial network. Later generations added gas, motion, lensing, and simulation. Each step removed another layer of apparent randomness. What once looked like scatter became structure. What looked empty became underdense. What looked isolated became embedded. There is a generational thread in that change. One group of observers measured galaxy positions by hand. Another built electronic detectors and automated surveys. Another developed algorithms capable of identifying filaments across datasets too large for any person to inspect individually. The instruments changed, but the underlying act remained familiar. Light arrived. Its direction was recorded. Its wavelength was measured. A place was inferred, then another, then millions more. The web emerged from accumulated attention. No one observation revealed it. The architecture became visible because measurements from different nights, telescopes, hemispheres, and decades could be placed within the same expanding map. This is how large structures often enter human knowledge. Not as a sudden image, but as a pattern assembled from partial views. The universe does not offer an external vantage point. We remain inside the thing we are trying to understand. The map must be built from within, and even now the largest surveys cover only portions of the observable cosmos with full detail. Some regions are hidden by the Milky Way's stars and dust. Some lie beyond present sensitivity. Some are known only through sparse tracers. The cosmic web we have mapped is both enormous and incomplete. Its visible branches continue beyond the survey boundaries. Its faint gas extends below detection limits. Its dark matter is inferred rather than seen. Yet the pattern is strong enough to remain recognizable through every method. Galaxies trace it, gas fills it, gravity reveals it, simulations grow it. The same architecture appears from different directions because it belongs to the universe, not to the technique. At the scale of a human life, the web seems motionless. No filament changes shape while we watch. No void noticeably expands across a lifetime. But scientific instruments can measure the consequences of movement, and models can connect one era to another. The static map becomes a slow film. Matter leaves open regions. Galaxies turn within halos. Groups travel along strands, clusters assemble at intersections. The universe continues organizing itself, even though the pace is too gradual for the eye. What appears fixed is only moving beyond our ordinary sense of time. The cosmic web is large enough to shape galaxies, yet delicate enough to preserve traces of the universe's earliest conditions. Its present form did not arise from gravity alone. Gravity required something to work with. The first density variations were not created by stars, galaxies, or clusters. They existed before any of those structures formed. Their origin belongs to the physics of the early universe, where small differences in energy and density were carried outward as space expanded. By the time the cosmic microwave background was released, those variations had become measurable patterns across the sky. Some regions were slightly warmer, some were slightly cooler. The differences were minute, but they marked the places where matter and radiation were distributed a little more densely or a little more sparsely. The later web grew from that pattern. This allows astronomers to compare two very different eras. The microwave background shows a universe that was young and nearly uniform. Galaxy surveys show a universe that is old enough for strong structure to have developed. Between them lies the long work of gravitational growth. A successful cosmological model must connect the two. It must begin with early fluctuations like those observed in the background radiation and evolve them into a distribution of galaxies, clusters, filaments, and voids resembling the universe today. The broad agreement is one of the reasons the modern picture of cosmic structure is so powerful. The model does not merely describe the current map. It explains how the map could have formed. Dark matter is central to that explanation. Its presence is inferred from many observations, including the motions of galaxies, gravitational lensing, the behavior of clusters, and the pattern of the cosmic microwave background. Within the web, dark matter provides most of the gravitational mass. It collects into halos around galaxies and clusters, while also forming broader bridges between them. Because it does not emit or absorb light in the usual way, its distribution must be reconstructed indirectly. Weak gravitational lensing is one of the most direct methods. The measured distortion of background galaxies reveals how total mass is projected across the sky. When these lensing maps are compared with galaxy maps, the two generally follow the same large pattern. Dense concentrations of galaxies coincide with strong mass concentrations. Filaments appear as lower density connections. Voids correspond to deficits. But the agreement is not perfect at every scale. Galaxies are biased tracers. They do not form with equal efficiency in all environments. And bright galaxies represent only part of the population. A region with a certain amount of dark matter may contain more or fewer visible galaxies depending on its formation history. Astronomers call this relationship galaxy bias. The phrase does not refer to an error in observation. It describes the fact that galaxies do not sample matter uniformly. A massive halo is likely to host a luminous galaxy or an entire group. A small halo may contain a faint galaxy. Some halos may host almost no stars. To use galaxies as tracers of the web, researchers must understand this connection between light and mass. That connection can be modeled statistically. The clustering of galaxies is compared with the clustering predicted for dark matter. Different populations are studied separately. Bright red galaxies, blue star-forming galaxies, quasars, and galaxy clusters each trace the underlying field in their own way. By combining them, astronomers can build a more complete picture. One especially useful feature in the distribution of galaxies comes from sound waves in the early universe. Before atoms formed, ordinary matter and radiation were tightly coupled. Gravity drew material inward, while radiation pressure pushed outward. This competition created waves moving through the hot plasma. When the universe became transparent, the waves stopped propagating in the same form. They left behind a preferred scale in the distribution of matter. Today, galaxies are slightly more likely to be separated by that scale than by nearby alternatives. The effect is called baryon acoustic oscillation. It appears as a statistical pattern, not as a visible ring around each galaxy. Across a large enough sample, the preferred separation becomes measurable. Because its physical scale can be predicted from early universe physics, it acts as a kind of standard ruler. Astronomers compare how large that ruler appears at different redshifts. The result provides information about the expansion history of the universe. This measurement does not require each filament or cluster to be understood individually. It uses the collective arrangement of matter across enormous volumes. The web becomes a cosmological instrument. Its spacing reveals expansion, its growth reveals gravity, its lensing reveals mass, its gas reveals heat and pressure, its voids reveal where structure did not form strongly. Several of these measurements are sensitive to dark energy. Dark energy is the term used for whatever drives the observed acceleration of cosmic expansion. Its physical nature remains uncertain. It may be related to energy inherent in space. It may reflect a field that changes over time. Some alternatives propose that gravity behaves differently across the largest distances. Current observations are consistent with a simple form, often represented by a cosmological constant, but the deeper explanation is unresolved. The cosmic web helps test these possibilities because accelerated expansion affects how quickly structure grows. Gravity pulls matter together. Expansion increases the distance between regions that are not gravitationally bound. If expansion accelerates, the growth of new large-scale structure slows. Dense regions continue evolving, but the rate at which they gather material changes. By measuring galaxy clustering, peculiar velocities, weak lensing, cluster abundance, and void statistics across time, astronomers can compare observed growth with model predictions. This is difficult because the signals are connected. A change in cosmology can alter distances. It can alter the rate of growth. It can change the apparent size of structures in redshift space. It can influence how many massive clusters form by a given era. Researchers therefore combine several methods to reduce ambiguity. The goal is not to make one measurement carry the entire conclusion. It is to see whether independent views of the web point toward the same underlying physics. Neutrinos also leave a subtle imprint. These particles are extremely light and interact only weakly with ordinary matter. They move rapidly through the universe, especially when they are young. Because of this motion, neutrinos do not cluster on small scales as readily as cold dark matter. They can smooth part of the matter distribution. The effect is slight, but large Galaxian lensing surveys can search for it statistically. The detailed shape of the web may therefore help constrain the combined mass of neutrinos. Particles, passing almost undisturbed through planets and stars, can influence how matter gathers across cosmological distances. This is another reminder that the web is not shaped by one ingredient. Its broad form reflects the balance of several components. Cold dark matter provides most of the clustering mass. Ordinary matter forms gas, stars, and galaxies. Radiation influenced early growth. Neutrinos suppress some small-scale structure. Dark energy affects late expansion. Gravity connects the entire evolution. The web is where these influences overlap. Because of this, researchers do not study only the most obvious structures. They also examine statistics that describe the field more completely. One measurement counts galaxy pairs at different separations. Another studies groups of 3 points, capturing shapes that pair counts miss. Others measure the abundance of voids, the length of filaments, the topology of connected regions, or the distribution of densities across a survey volume. Topology is especially useful because it describes connectivity. It asks how many isolated high-density regions exist, how many tunnels run through the structure, and how low-density spaces connect. A simple comparison of average density might miss these features. Two universes can contain similar amounts of matter while arranging it differently. Connectivity reveals the difference. The cosmic web can also be studied through a mathematical idea called persistence. Small features may appear or disappear depending on how a density threshold is chosen. Strong features remain identifiable across a wide range of thresholds. A major filament connecting two clusters persists. A weak fluctuation near the noise level does not. This helps separate meaningful structure from accidental patterns in incomplete data. The need for such methods reflects the scale of modern surveys. Earlier maps contained thousands of galaxies. Current and planned surveys contain millions, and in some cases far more. No person can inspect the full structure by eye. Algorithms identify filaments, estimate distances, correct instrumental effects, and compare the observed field with large suites of simulations. Machine learning can assist in classification and reconstruction, but its results must remain tied to physical interpretation. A network may detect a pattern accurately without explaining why it exists. For cosmology, prediction alone is not enough. Researchers need to know which features of the data support which physical conclusion. The cosmic web is therefore studied through both computation and theory. The computer finds structures too numerous for manual inspection. The theory explains why those structures matter. Observation tests whether both are correct. Future surveys are designed to deepen this comparison. They will map galaxies across larger areas and greater distances, measure shapes for weak lensing, identify clusters through several wavelengths, and trace hydrogen in both emission and absorption. Radio telescopes can map neutral hydrogen through its characteristic 21 centimeter signal. At later cosmic times, individual galaxies may be detected. At earlier times, researchers may measure the combined emission from many unresolved systems, building a statistical map known as intensity mapping. Instead of finding each galaxy separately, the telescope records the total signal from broad regions. Subtle variations then trace large-scale structure. This approach sacrifices detail about individual objects in exchange for rapid coverage of enormous volumes. The method suits the cosmic web because the web is fundamentally a collective pattern. Its most important information often lies not in one galaxy, but in how many galaxies and gas clouds relate across distance. Other instruments will examine the hot and warm gas more directly. Sensitive X-ray observatories may detect faint emission from filament interiors. Improved ultraviolet spectroscopy can search for absorption by ionized elements along more sightlines. Microwave measurements can map pressure and motion through scattering effects. Gravitational lensing surveys will provide broader mass maps. Each new layer will reduce the gap between the visible galaxy network and the fuller distribution of matter, but complete visibility may remain impossible. Dark matter does not shine. Much of the gas is extremely thin. Many galaxies are faint. Some regions lie behind foreground dust or outside practical survey limits. The web may always be partly reconstructed rather than simply seen. There is no failure in that. Astronomy has often learned through indirect effects. A planet is found by the motion of a star. A black hole is inferred from orbiting matter. An element is identified through missing wavelengths. The cosmic web is known through clustering, absorption, lensing, pressure, motion, and simulation. Its reality does not depend on appearing as one luminous object. It is confirmed by many separate traces agreeing on the same structure. That agreement also makes the web a record of time. A survey at one redshift shows one stage. Another survey farther away shows an earlier stage. The microwave background supplies the initial pattern. Simulations connect the frames. The result resembles a history assembled from light that left at different moments. There is no camera outside the universe recording the development. The archive is carried within the universe itself. Older light comes from farther away. Matter preserves gravitational consequences. Galaxies retain signs of their environments. Gas carries heat from collapse and feedback. Voids remember where density was low. The web is both architecture and memory. It contains the outcome of processes that began before the first stars and continued through every era of galaxy formation. It also contains limits. The farther astronomers look, the less mature the structure becomes, and the more difficult the measurements are. The earliest filaments may be traced only through sparse galaxies or absorption against rare background sources. Some of the first connections remain below current sensitivity, yet even incomplete observations can test whether growth proceeds as expected. A young web should be less contrasted. Its nodes should contain less assembled mass. Its filaments should be narrower or less populated. Its galaxies should be receiving gas more actively. These predictions can be compared with distant surveys. When the observations agree, they strengthen the physical picture. When they do not, the difference may reveal missing astrophysics, measurement bias, or a deeper problem with the model. The cosmic web is valuable, partly because it can fail to match our expectations. A scientific map is not merely an illustration, it is a test. Every filament location, every clustering scale, every lensing pattern, and every void distribution becomes a question posed to the model. Did gravity grow structure at the correct rate? Does dark matter behave as assumed? Do galaxies occupy halos in the predicted way? Is the expansion history consistent across methods? Do neutrinos leave the expected suppression? Does ordinary matter reside where simulations place it? The answers are rarely absolute. They arrive as ranges, likelihoods, tensions, and agreements. The language may sound less dramatic than discovery, but it is how a precise picture is built. A single result can be affected by calibration or sample choice. A network of results is harder to misread. That is fitting for the subject. The cosmic web itself gains strength through connection. One strand alone reveals little. Many strands reveal the architecture. One measurement offers a clue. Many independent measurements begin to reveal the physics beneath it. The cosmic web does not end at the edge of what we can currently map. Its filaments continue beyond survey boundaries. Its faint gas extends below the reach of present instruments. Its dark matter remains known mainly through the gravity it contributes. What we see is a partial reconstruction from inside structure itself. That limitation is not unusual in astronomy. No observer can step outside the Milky Way to photograph its full shape. No instrument can watch a galaxy evolve across billions of years. No telescope can view the universe from beyond its horizon. Knowledge is assembled from light, motion, chemistry, geometry, and time. The web has emerged from that assembly. It first appeared as an uneven distribution of galaxies. Then redshift surveys gave the pattern depth. Quasar spectra revealed hydrogen between the galaxies. Gravitational lensing traced mass that emitted. Microwave measurements exposed pressure in thin gas. Simulations connected the young universe to the mature network around us. Each method found a different part of the same architecture. The result is no longer only a picture of where galaxies happen to be. It is a history of how matter moved. Slightly denser regions drew material inward. Underdense regions gave up part of their contents. Sheets narrowed into filaments. Filaments fed nodes. Inside those nodes, clusters assembled. Within the clusters and along the connecting strands, galaxies formed, collided, lost gas, gained gas, and changed. The web did not merely hold these events. It helped determine where they occurred. Even the Milky Way belongs to this history. Our galaxy formed inside a dark matter halo within a local environment shaped by neighboring structures. The local group moves through a broader gravitational field. Nearby concentrations attract it. nearby underdense regions provide less opposing pull. The solar system is carried through that motion without sensing it directly. Earth circles the Sun moves through the Milky Way. The Milky Way and Andromeda approach each other within the local group. The local group follows the influence of structures spread across distances far larger than either galaxy. These motions do not require a central destination. There is no single point toward which the whole universe is falling. Different regions respond to different gravitational surroundings, while the overall expansion continues between structures that are not bound together. The web evolves through this balance. Gravity gathers, expansion separates. Dense regions resist the expansion more effectively. Open regions become broader. At the present cosmic era, the contrast between them is strong enough to map across immense volumes. Far into the future, that balance will continue to change. If accelerated expansion persists, distant structures not held to us by gravity will recede ever more rapidly. Their light will stretch toward longer wavelengths. Over immense time, many will pass beyond the region from which new signals can ever reach our descendants. The connected web visible today will become harder to recover from any one location. Local groups and clusters that remain gravitationally bound will endure as isolated regions, while the broader network fades from observational reach. The web itself will not suddenly break. Its distant sections will simply become inaccessible to one another. An observer in that future may look outward and see a much emptier cosmos. Without records from earlier eras, the evidence for the larger network could be difficult to reconstruct. We live during a period when the architecture remains widely visible. Light from distant filaments is still arriving. The cosmic microwave background still crosses the sky. Galaxies at many stages of evolution can still be measured. Clusters, voids, and developing structures remain present within the same observable volume. This makes the current universe unusually informative. It carries the early pattern, the mature web, and the ongoing flows between them. The evidence is spread across wavelengths and timescales, but it has not yet slipped beyond reach. There is no need to imagine the full network all at once. The scale is too large for a single mental image to remain accurate. It may be enough to hold one relationship. A galaxy is not alone. Around it lies a halo. Beyond the halo lies diffuse gas. Beyond that gas lies the filament. The filament joins other structures. Those structures surround voids and converge at nodes, and every level is connected through gravity to a history that began when the universe was almost smooth. The bright objects are only the parts that announce themselves. Most of the architecture is dim. Some of it does not shine at all. Yet the invisible components are not separate from the familiar sky. They shape the motion of the galaxies whose light reaches our eyes. They guide the gas from which future stars may form. They influence where clusters gather and where matter becomes scarce. The unseen framework and the visible universe are one system. A star inside a distant galaxy may appear as an isolated point within its own local night. The galaxy around it may seem like the complete world, but that galaxy is moving within a larger environment, connected to matter far beyond its own luminous edge. Its position was influenced before its oldest stars formed. Its future may depend on a filament it cannot see from within. The same is true of our own location. The night sky presents separate lights because distance hides the connections. Astronomy restores some of them. A redshift links a galaxy to depth. A lensing distortion links light to mass. An absorption line links a quasar to foreground gas. A velocity links a galaxy to the gravitational terrain around it. A simulation links a present structure to an earlier fluctuation. The web becomes understandable through relationships, rather than through any single object. That may be its most important perspective. The universe is not organized as a collection of independent islands. Its structures emerge from shared beginnings and continuing influence. Matter moves along gradients created by other matter. Galaxies grow from material drawn through their surroundings. Voids widen as their contents travel outward. Clusters assemble from streams arriving over billions of years. Nothing needs to know the pattern for the pattern to form. Gravity acts locally. The architecture appears globally. From within one small galaxy, on one planet near one ordinary star, instruments have begun to trace that result. They have measured enough galaxies to reveal the strands, enough background light to detect the gas, enough distortion to map the hidden mass, enough early radiation to recover the seeds. The picture remains incomplete, but its main form is clear. The cosmic web is the large-scale arrangement of matter in the universe. It is also a record of transformation. Nearly uniform beginnings became contrast, small fluctuations became clusters, diffuse material became stars. Open regions became voids, invisible gravity became visible structure, and the process continues now, beyond the pace of direct perception. Galaxies are still moving along filaments, gas is still falling into halos, clusters are still gaining members, voids are still expanding into the spaces around them. The map is alive only in the slowest physical sense, changing across spans that exceed civilizations and species. For a listener resting beneath the night sky, none of that motion asks for attention. The structure continues without effort from us. Light keeps arriving from galaxies, embedded in distant strands. Gravity keeps shaping paths across regions no person will cross. The planet turns within its local part of the network, carrying oceans, cities, sleeping rooms, and every familiar thing through a universe held together by connections too large to see directly. Above the atmosphere, the stars still appear separate. Beyond them, the hidden architecture remains joined. The web holds its shape among the stars.